This video is about moment generating functions, MGFs. We know moments are pretty useful in characterizing random variables. The case moment for a given real-valued random variable will be equal to the expected value of x to the power k, if such value exists, right? But there are so many of those moments. Now let's consider a problem. For a given real-valued random variable, if all the expectations of its powers are well defined, then we have a sequence of moments. This is a sequence of specific numbers of infinite length. So can we find something else to work with this sequence, to store the information within a sequence of moments? So this is a specific sequence of numbers, and the number changes as the power increasing from 0, 1, 2, 3, 4, and keep going. There is something else that also varies with the powers, which will be the polynomials, right? And each polynomials of different powers, here is t to the power 0, t to the power 1, 2, 3, 4, they are of different shapes. They are unique functions. So we can encode each moment with one associated unique polynomials. We can use polynomials to store this information. We're going to label each moment with a unique polynomial. We're going to multiply them together. And we're going to sum them together. Then for a given t, we have a summation of infinite series. If this summation is well defined, if this summation has a limit, right? So this is the summation of infinite series. If this summation is well defined, surprisingly, it is equal to the number expected value of e to the power tx. Now let's suppose this number is well defined, is finite, right? If this summation is well defined, then this number is well defined. So for each given t, we can find a number to assign to this t. This is a function. And now from a sequence of number, we have a function, and working with functions is so much easier compared with working with a sequence of numbers of infinite length. This is the moment generating functions we are going to work with. Of course, we know the expectation value here may not be well defined for some t, so we need to be specific about when this function, the moment generating function of this, we need to discuss when this moment generating functions concerning a specific random variable is well defined or not, right? Normally we use mx to denote the moment generating functions of a given real valued random variable x, and this maps some value t to the number expected value of e to the power tx. When is this function well defined? Well, we say it is well defined if we can find a positive a such that this function will take finite values for any t within this open intervals, within this open interval from minus a to a. If we can find such a, and the moment generating functions only take finite values for t from this open interval, then we say this moment generating function for the given real valued random variable x is well defined. Namely, this function is only well defined if the summation below is finite, right? This is the summation below for any t from some given open interval containing 0. And 0 here is an essential value we need to work with when it comes to the moment generating function. Later on, we're gonna show why. Let's for now discuss why this summation of infinite series is essentially equal to the same number of expected value of e to the power tx. Let's take a look at this summation on the left-hand side, right? If this summation is well defined, this is a summation of numbers, right? Expected value of x to the power I is numbers. For given t to the power I is numbers and divided by I factorial. So this is a summation of numbers. However, based on if this summation is well defined, then we can make use of the linearity of expectation, and we're gonna change the order of the summation and expectation, right? Let's take a look of the summation of infinite series on the left hand side first. It can be rewritten first by the linearity of expectation. We can move the constant inside the bracket, right? So this summation of infinite series is also equal to the summation of expected value of this new random variable x to the power I times ti divided by I factorial. If this summation is well defined, now we can interchange the order of the summation and the expectation using the linearity of expectation. This gives the formula in the middle. So the summation here, if the summation on the left hand side is well defined, then essentially it will be equal to the number expected value of this new random variable. This is the summation of x to the power I times ti divided by I factorial and sum over I from 0 to infinity. This is the function of random variable x. So it's a new random variable. Now we claim this new random variable here, this monster here, is essentially equal to e to the power tx, which is also a function of random variable x, a random variable. And this summation, this random variable, let's denote it as a, is essentially equal to b. A and b, they are the same random variable, right? Why do I make this claim? You can pause the video at this moment and think about yourself. The claim I made is the random variables here, x to the power I, ti divided by I factorial, is essentially equal to this random variable, right? So on both sides of this identity, we have two different random variables. Both are functions of the random variable x. I claim these are the identical random variables on both sides. This identity holds true because they are essentially the same functions from the underlying sample space to numbers. Suppose we have a small s from the sample space such that x maps small s to an arbitrary number, let's say arbitrary number a. What will be the number given for the from the left-hand side of this identity? Well, let's take a look what this number will be, okay? So the random variable on the left-hand side of this identity, for the given some outcome, we know it will be equal to, well, for the given outcome, we know xs is equal to number a, ti divided by I factorial. This will be equal to, now a is just a number, so this is the summation of 0 to infinity, at to the power I divided by I factorial. For given t, at is a number, and this summation is essentially equal to e to the power at. This is exactly the number that the function gonna map to for the given outcome small s, right? Because e, if we look at the random variable on the right hand side, it will also map this arbitrary s from the underlying sample space to the same number, e to the power at, exponential at. So on both sides of this identity, they all map the same outcome from the underlying sample space to the same number. Therefore, they are the same random variables. Then if we take expectation on both sides, they will be equal to the same number, right? Expectation will assign the same number to the same random variable. Therefore, we have this identity here. And this is how we define the moment generating function. The moment generating function, if it's well defined, it should take value e, expected value of e to the power tx for given t, right? In some open intervals, in some open interval containing 0. Let's take a look one example to see how these moment generating functions can be calculated, derived for a given random variable. So let's consider exponential distributed random variable. Suppose we have a random variable x, which follows exponential distribution with parameter 1, with arrival rate 1. Then let's calculate the moment generating function value for a given t. It should be equal to the expected value of e to the power tx. Right now we apply the law of the unconscious statistician. This is essentially the integration of e to the power t small x times the density. We're gonna integrate over the support of the exponential distributed random variable. It only takes non-positive values, so it's from 0 to infinity. And the integration result is 1 over 1 minus t. For any t that is not equal to 1, this is well defined. Therefore, note this function is finite, for example, for t from minus half to half. So we have an open interval that contains 0 such that this function is well defined. So this moment generating function is well defined. Okay. Particularly when t is equal to 0, this function always equal to, right? Always equal to 1, because e to the power tx, if t is equal to 0, under t equals to 0 is always e to the power 0 is always equal to 1. Okay. So this is the example how a moment generating function can be calculated for a given random variable, and particularly note that when you have done the calculation, always check whether the moment generating function is well defined or not. Right? Because for some random variables, unfortunately, we don't have moment generating functions. The logic is exactly the same, that expected value just expectation values just do not exist for certain type of random variables. Now we have a question. If we have the moment generating function equal to each other for random variable x and y in some interval containing 0, in some open intervals containing 0, what do we know about the moments, the nth moment of x and the nth moment at y? Well, given moment generating functions containing all the information of the moments, not surprisingly, we will have the result that all the nth moment of x and nth moment of y will be equal to each other. Actually, we know a bit more, that x and y will have identical distribution, but we'll figure that out much later. Let's first discuss the equality between these two numbers, the nth moments of x and the nth moment and y. Okay? So how do we prove that? The argument is quite straightforward. We're going to make use of the linearly independence of polynomials. Suppose we have a summation of polynomials, right? The summation of polynomials is ai over I factorial times ti. if this is equal to 0, if this value is equal to 0 for some t in some open interval containing 0, this gonna imply that AI has to be 0. So, therefore, if we have two moment functions, moment generating functions equal to each other, if we have two random variables, x and y, they have identical moment generating functions for t in some open interval containing 0, that basically means they are taking exactly the same values for those t. This summation of infinite series will be equal to each other, right? Based on the definition of moment generating functions. Now we combine both sides together, which will be the difference of xi, the nth moment of xi minus the nth moment of yi times fact t to the power I divided by I factorial. This one will have to be equal to 0 for some t from the open interval from some open interval containing 0. And based on the linearly independence of polynomials, we know this AI, in this case, AI is equal to the ith moment of x minus ith moment of y. They have to be equal to each other, right? This one has to be 0. So this ith moments of x and y has to be equal to each other. So if we have identical moment generating functions for t from some open interval containing 0, then the associated random variables, they will have exactly the same nth ith moment. This is not surprising result. This is not a surprising result because we know moment generating functions encode all the information for a sequence of moments. Right? If we have the same function, we should have the same sequence of moments. Indeed, we can derive moments from the MJF if this MJF function exists, if it's well defined. Because the information of all moments are encoded in the MJF function by design. We can derive moments from the MJF. Commonly, there are two ways to go. The first way is we're gonna take nth derivative with respect to t and evaluate the nth derivative function of the moment generating function at t equal to 0. Now see, we're gonna plug in 0, which is why we always emphasize that, right? MJF function you need to check that it's well defined for any t's from some open interval containing 0. Now we are making use of the 0. So the nth derivative function of the moment generating function evaluated at t equal to 0 will give the value which equals the nth moment of a given random variable. So if the MJF function of x is well defined, then we can always recover its nth moment. You can pause the video at this moment and try to figure out the proof. It's not very hard, actually. Now, we show the sketch of the proof. So notice, by definition, we know the moment generating function is equal to the expected value of e to the power tx. If it's well defined, if this value is well defined for given t, we know it's also equal to a summation of infinite series. Right? This is a summation of numbers for given t. So this summation is also a function of t because it gives different numbers for different t, right? It's a summation of infinite series of numbers for given t, and for each given t, it delivers different numbers. if well-defined. So what is the nth derivative function of the moment generating function? We're gonna take nth derivative with respect to t. That is the same as taking nth derivative with respect to the summation of functions, of polynomials. If the moment generating function is well defined, we can interchange the order of the taken derivative, nth derivative, and the summation. So the nth derivative of the summation of polynomials is essentially equal to the summation of nth derivative of each term of each polynomials inside the summation. Look at here, for any I that is strictly smaller than n, the nth derivative of the polynomial is essentially equal to 0, right? You can easily check that. What is the, for example, third derivative of t to the power 2? That is essentially equal to, let's first take first derivative, and then we're gonna take the second derivative with respect to the first derivative. This is equal to 2t, and then we took the second derivative of the 2t, which will be taking first derivative first, and then we're gonna take the first derivative with respect to the first derivative, which will be the first derivative of a constant that is always 0. Right? So for any I that is strictly smaller than n, the nth derivative will be equal to 0. And if I happens to be equal to n, then this is the value you get in the end. Right? You can easily verify whether this is true or not. So this is simply a number divided by n factorial. Let's take nth derivative. In the end, we will find the nth derivative of this polynomial is equal to this number, the nth moment of x. And for the remainings, this is the results. For any I that is strictly larger than n, this is what's left after you take nth derivative. So this is our targeted value. Now if we plug in t equal to 0, this contains t to some positive powers, right? If t is equal to 0, it's just a summation of many zeros. It's gone. Therefore, the nth derivative function of the moment generating function evaluated at t equal to 0 will deliver the value of the nth moment of x. This is the first way that we can to derive moments, nth moment of x based on the moment generating function of x. Second one, we can also make use of the Taylor expansion or other expansions. We're gonna rewrite the moment generating function in this format. So basically, this is the function of t, and make use of Taylor expansion or other approaches of expanding a function. Let's rewrite this function as a summation of polynomials in this format. And an is our targeted value, which will be the nth moment of random variable x. So these are the two ways to derive moments from a given moment generating function. Let's take a look at one example. Again, we work with exponentially distributed random variable with arrival rate 1. Let's consider working with expansions. We have already calculated the moment generating function for such x following exponential distribution with arrival rate 1, right? Which is equal to 1 over 1 minus t. This is well-defined moment generating function, as this one takes finite values for any t, for example, in open intervals -1 to 1, for example, right? This takes finite values, so we know this moment generating function is well-defined. Now let's rewrite it as a summation. Here we can make you can make use of Taylor expansion, or you simply use geometric series summation. We know this one will be equal to a summation of t to the power I here. Let's denote for the consistency, let's use n here. So this is a sum of t to the power n from n equals to 0 to infinity. And let's rewrite it as in the format such that it's a constant times t to the power n divided by n factorial. Then this n factorial will be our targeted value, right? So based on this format, let's compare with the definition we have for the moment generating function. We know this is the value we are looking for, the expected value of x to the power n. The nth moment of x should be equal to n factorial. Of course, we can also make use of the second way, taking derivative and evaluate at 0, right? Then it basically means let's taking derivative of 1 over 1 minus t and plug in t equal to 0. What is the nth derivative of this moment generating function? That will be essentially the nth derivative of the function 1 over 1 minus t. It will be equal to this value after you take in the nth derivative. Now let's evaluate this nth derivative function at value 0. So we plug in t equal to 0. What's left is n factorial divided by 1. 1 minus t to the power 1 minus 0 to the power n plus 1 is 1. So it's n factorial, right? There are two ways to recover the nth moment of a given random variable. So indeed, based on these two, both approaches work, and both deliver exactly the same result. Right? You can choose one you like to work with and to derive moments for given x. Normally, the second approach is easier, right? We just take in derivative and plug in value t equals to 0 to the nth derivative. Then you have the result. So from the moment generating functions, we can deliver the moments. And now it's also easier to calculate all the other values. For example, the variance of x. Right now you can calculate all the moments already, and now we just plug in what we know. So nth moment of x is n factorial, and the variance of x is the second moment minus the squared first moment. We plug in the numbers. It gives the variance of a exponentially distributed random variable x with a arrival rate 1. The variance is simply equal to 1. Actually, moment generating functions, if you find one, if you already have the moment generating function, it does not only determine moments, it actually, if it exists, it determines the distributions. Right? If two random variables have the identical moment generating function, they have the same distribution. Previously, when we check the distribution type of given random variables, we always look at their distributions. But now we can also look at the moment generating function, right? If the moment generating function exists, if two random variables have similar type moment generating functions, their distributions are also will also be of the similar type. Now let's take a look at some examples. This is very useful when we're dealing with when we deal with sum of independent random variables. Here again, independence means products. This is the formula we're gonna make use of in the following examples, right? If we have independent and x and y, then their summation, the moment generating function of the random variable x plus y is essentially equal to the product of the moment generating function of x multiplied by the moment generating function of y. So in order to know the distribution of x as x plus y, we can look at their CDF, PMF, or PDF, but we can also look at its MGF, moment generating functions. And when we have summation of independent random variables, normally we'll choose to look at the moment generating functions, because with the formula here, it's very easy to deal with that. Now let's proceed to the examples. Example 1. Show that a sum of two IID exponentially distributed random variables with a readable rate 1 is not exponentially distributed. You can pause the video at this moment and try to figure out how would you derive this, making use of the moment generating function. Well, to work with moment generating function, of course, we need to first derive all the moment generating functions. The MGF of a exponentially distributed random variable with a rival rate lambda, again, we calculate by definition. It should be for given t. This moment generating function should assign this value to the given t, right? Expected value of d to the power tx. Then, based on the law of the unconscious statistician, this expected value is simply the Riemann integral of e to the power t small x times the density evaluated as the small x. We're gonna integrate this product through the support of the exponentially distributed random variable, which is from 0 to infinity. This gives the results 1 over lambda minus t. Now we check whether this moment generating function is well defined or not. Well, given we ask this question in the example, we know it's well defined, but it never harms to double check the validity of the moment generating function, right? So this function 1 over lambda minus t is finite, for example, for any t in this open interval containing 0. So the MGF function is well defined. Now we have the MGF function of a exponentially distributed random variable. Let's proceed concerning the summation of two exponential distributed random variables. The moment generating function of y plus y1 plus y2, if they follows IID exponential distribution, based on the formula we have from previous slides, independence means product. The moment generating function of y1 plus y2 evaluated at t is essentially equal to a product of y, a moment generating function of y1 at value t, and moment generating function of y2 at time t. We're gonna multiply them together. Here lambda is chosen to be 1, so this will be 1 over 1 minus t times 1 over 1 minus t, right? These two are identical because they follows IID distribution, independent and identical distribution. Again, this is well defined, right? For example, for t in this open interval containing 0, this value here, this function value here, the function values in this open interval will always be finite. So the moment generating function is well defined. But take a look over the moment generating function of a general exponentially distributed random variable. We see these are of different type. The moment generating functions are different. So the summation of two IID exponentially distributed random variable with arrival rate 1 cannot be exponentially distributed, right? Because moment generating functions determine distributions. Now let's see that indeed 1 over 1 minus t to the power 2 cannot be written in the form of 1 over lambda minus t for any lambdas. We prove this by contradiction. Suppose they are equal for some lambda, then let's pick up t equal to 0. They should be equal to each other for such lambda. Therefore, the lambda has to be equal to 1, right? If you plug in t equal to 0, the right-hand side, the left-hand side here is equal to 1, and the right-hand side here is equal to 1 over lambda. So lambda has to be equal to 0. However, if we choose any arbitrary t here, apparently 1 over t evaluated at t equals 1 over 8 is not equal to 1 over 1 minus t, with t chosen to be 1 over 8. So we have two different types of moment generating functions. The moment generating function of y1 plus y2 is not the moment generating function of any exponential distribution. Therefore, we know a sum of two IID exponentially distributed random variable is not exponentially distributed, because we know the moment generating functions determine distributions, and different moment generating functions would mean different distributions. In the calculation, this is quite important, right? And why do we have this product? Why the moment generating function of the sum of independent random variables is equal to the product of moment generating function? If we go back to the previous slides, that is essentially roots out from this fact. This is the definition of the moment generating function of the sum of x plus y. Now, if x and y are independent, we know these functions of random variables, exponential x, exponential y, they are also independent from each other. And when we have independent x, y, independence always means products. If we have ex and ey independent from each other, the expectation of the product will be equal to the product of the expectation of each expectation. Okay, now if we look at here, this is the moment generating function of mx, and this is the moment generating function of y, my. So this is why I say that when we have sum of independent random variables, it's always easier to work with moment generating functions to determine the distribution type. Hopefully from the first example, you already get some idea that it's easier to work with moment generating function. Let's take a look at example 2. Now, let's show that this binomial distribution can be perfectly approximated by Poisson distribution with a arrival rate lambda as n increasing. This is a specific case of Poisson diagram, right? In the Poisson diagram, we know the Poisson distribution serves as a nice approximation for the distribution of many Bernoulli distributed random variable with more successful rate if they are IID. And here, binomial distribution is also equal to a summation of i from 1 to n, and here the successful rate for each I, pi, the successful rate is also quite small. And from the Poisson diagram, we know Poisson distribution should serve as a nice approximation when n is very large and pi very small, which is indeed the case here. So how do we prove this statement? Making use of the moment generating function, you can stop the video at this moment and try to figure it out yourself. the proof is straightforward. Again, we check different moment generating functions, but here's quite many. We first need to derive the moment generating function of a binomial distributed random variable. And we also need to deliver the moment generating functions of the Poisson distributed random variable. Then we can compare their format in the limit. So let's first derive the moment generating functions of this binomial distributed random variable, of this binomial distribution. To work directly with the binomial distribution is a bit hard, but we know, well, binomial distribution is the summation of IID Bernoulli distributed random variable with successful rate p, right? Let's here work with generic p, and later on we're gonna plug in p equals to lambda over n, right? Let's first work with p. Why do I work with Bernoulli distribution? Because we know the summation of xi will follow binomial, and the moment generating function of the summation is simply the product of each individual moment generating functions if they are IID, if they are independent random variables. And it's so much easier to work with the moment generating function for Bernoulli distributed random variable, which is simply this format. Why is the case? Because based on the definition, what is the expectation of e to the power t xi? So it basically, xi either takes 0 or 1, right? And it takes 0 with probability 1 minus p, and e to the power 0, right? 0 times t is simply 0 is 1 plus xi equals 1, then with probability p, and 1 times t is equal to t, right? So essentially this is 1 minus p plus e to the power t times p, which is p times et minus a minus 1 plus 1. Note this function is well defined for any t from the real line. So for sure, this moment generating function is well defined. Okay, now what is the moment generating function of the binomial distribution with n and successful rate p? We know the summation of xi follows binomial distribution. Then given the fact that distributions determine moments, moments give us the moment generating functions, and here the summation follows the binomial distribution. So for any binomial distributed random variable, the moment generating functions, right, we can calculate directly based on the summation of xi. They have the identical distribution, they have the same moment generating function. If they have the same moment generating function, they have the same distributions. You see the nice connections here. So let's now work on the moment generating function of the summation of IID Bernoulli distributed random variable xi. Again, we make use of the fact that the moment generating function of the sum of independent is simply the product of each individual moment generating functions. So here, given we have a summation of n terms, right, this gonna be a product of mx1 times mx2 at t and mxn at t. And we always use this notation to denote the product from I equals 1 to n, right? Okay, now we plug in the moment generating functions we derive in the first step. They are identical to each other, right? They are identical to each other because they are IID distribution, distributed random variable. So each of the mxi is essentially equal to mx1. They have identical distribution, and identical distributions lead to identical moment generating functions. And we plug in the moment generating functions we derive. This is the moment generating function for the binomial distribution. Again, this is well defined for any t from the real line, so the moment generating function is well defined for the binomial distribution with n and p. Now we derive the moment generating function. What else do we need to derive the moment generating function of the Poisson distributed random variable, right? Let's consider that which follows the Poisson distribution with arrival rate lambda. And again, right, by definition, we know the moment generating function is defined as the expected value of t to the power of e to the power tz, and which will be a weighted sum of all possible value taken by this random variable exponential tz. Then by the law of the unconscious statistician, we know is simply e to the power tn multiplied by the probability of that equals n. Now we combine things together, right? So e lambda does not change for any different n's. We move it outside the summation, and we combine e to the power tn and lambda to n together. That it will be lambda times e t to the power n, and divided by n factorial. What is the summation here? If we still recall the fact that E lambda is equal to the summation lambda, let's use lambda tilde here. And from 0 to infinity. Note here the lambda tilde in this case is equal to lambda times e to the power t. So this summation is equal to, well, e to the power lambda et. And if we combine them together, this is the moment generating function we have for a Poisson disputed random variable with a arrival rate lambda. And this moment generating function is well defined for any t from the real line. So this moment generating function, all right, this value is finite for any t from the real line. So this moment generating function is well defined. Next is the interesting step. Note that in the limit, those two moment generating functions coincide with each other. Okay. Now we plug in the fact that we choose p to be equal to lambda over n. So the limit here is equal to 1 plus lambda times e to the power t minus 1 divided by n to the power n. And now we are making use of the fact that 1 plus 1 over n to the power n goes to e. And if we have an arbitrary a here, if n goes to infinity, this value will goes to e to the power a. And a in this case is equal to this lambda times et minus 1. So in the end, this limit goes to, well, surprisingly, it goes to the moment generating function of a Poisson distributed random variable, right? Those two moment generating functions coincide in the limit. And we know same MGF, same distribution. So the MGFs are the same in the limit, which implies in the limit these two distributions coincide. That is why the Poisson distribution serves as a very nice approximation for the binomial distribution in specific case, when we have a large n and a very small successful rate, right? If n is very large, lambda over n for a fixed number lambda is very small. So this is the second example we give. Let's take a look at the third example. And this time, please try to prove it yourself, right? It's not very hard to work with moment generating functions. So now let's show that a sum of n independent Poisson distribution with a arrival rate lambda I with I from 1 to n is still Poisson. So a sum of n independent Poisson distribution. Now each distribution is slightly different. They all follow Poisson distribution, but with different arrival rate lambda I. From the previous example, the example 2, we have already derived the moment generating function of the Poisson distributed random variable, which is e to the power lambda times et minus 1. Right? This is well defined, for example, because it takes a finite value. This function takes finite value for any t from this, for example, open interval containing 0. It's actually well defined for any lambda from the real line, but we only need to check it's finite for any values within a open interval containing 0. Then we can see the moment generating function is well defined. Okay, so this moment generating function is well defined. You can pause the video at this moment and try to figure out how to proceed. Well, the summation, now we have a sum of independent random variables. So the moment generating function of the summation of independent random variable is essentially the product of each of the moment generating function with respect to each term within this summation, right? This is the random variable constructed by a summation of n independent random variables, and the moment generating function of this summation of this summed random variable is essentially equal to the product of each moment generating functions concerning each term in this summation. We have already calculated the moment generating function of general Poisson distributed random variable with a arrival rate lambda. Now, what is the moment generating function for a yi? We just plug in. So here the moment generating of the summation is the product of the individual moment generating function. And we know yi is the Poisson distribution with arrival rate lambda I, so we just plug in lambda I here. See, it's very easy to work with summation when we work with moment generating functions. Now, what is this product? The product of e to the power lambda I times this et minus 1 is essentially equal to e to the power of the summation. Now, if we compare the format of the MGF function of a general Poisson distributed random variable with a arrival rate lambda, and here, this is also well defined, for example, for any t in this open interval. So the MGF of the summation of the new random variable here, the sum of yi's, is also well defined. And note, this is a moment generating function if you have arrival rate equals to the sum of lambda i's. Right? If we compare those two moment generating functions. So if we choose lambda tilde, in the second case, we are simply having lambda tilde equals the summation of lambda i's. This is exactly in the format of the moment generating function of a Poisson lambda distribution. So the moment generating functions of this summation is the moment generating function of a Poisson distribution with a arrival rate, which simply sums all the arrival rates together. Then we know a sum of n independent Poisson random variable lambda I is still Poisson. It actually follows Poisson distribution with the arrival rate that equals the summation of all the arrival rate lambda i's. So in this video, we discuss the moment generating functions, the definition, and especially its applications, right? We could derive moments based on the moment generating function. We can also use moment generating functions to check the distributions, especially for the summation of independent random variables. Thank you for watching this video.